It's my pleasure to welcome Alex Suciu of Northeastern University, who will speak to us today about Dwyer-Fried invariants.
Thank you, Dave. It's nice to talk here. All right, so let me start. X will be a connected CW complex in all this talk. Say with finite, oh, look at this chalk, one skeleton. Okay, although most of the time you can think about a finite CW complex. So I'll take G to be pi 1 of the space, base that I say x0 equals single zero cell. We can, without loss of generality, we can assume there is a single zero cell. And we will look at all, say, regular Galois covers of X with group of deck transformations equals z to the r. Okay, for some fixed r. Let's say between, to have such covers, the R has to be at most B1 of X, which I would always denote by N. All right. All right, so, and also there will be, say, connected all the covers. All right. So how do these covers come? Okay, so the model situation. Well, you have R to the R. I should use a different letter there. So this is the R torus, and its universal cover is R to the R, which is a free abelian cover. And then you have this X, and then there is a map here, a classifying map, and this pulls back. Let me just write it like this. Okay, so, all right, so model situation is this one. Okay, so get any such cover of X by pullback. Okay. Okay. Okay, determined by along F. Okay, where nu is, this is the nu here, is a map from G to Z to ZR, an epimorphism. Okay, and F sharp from pi 1 of X to pi 1 of T to ZR equals to nu. All right? So maybe I didn't say it in the right order. Let me try one more time. So how do you classify covers? They are classified, these are regular covers, okay? So they're given by normal subgroup of the fundamental group, okay? With quotient group Z to ZR. So the normal subgroup would be the kernel of nu, where nu is an epimorphism from G to Z to ZR. Okay, so that's the general classification of covering spaces. And how do you do this? You realize this epimorphism by a map, a continuous map from X to the torus, and you pull back this universal cover of the torus. Okay, so all such covers are obtained this way. Okay, so that's just covering space theory. And so just note, X to the nu is the homotopy fiber. Of F. Okay, so up to homotopy, this is, for example, this is a fibration. X to the nu is a homotopic to the fiber of this fibration. Okay, so let me just kind of give you an example, just for Dave.
Some singular space, please.
So what would be kind of an example that appears in singularity theory? The Miller vibration. So how does the Miller vibration come up in here? So let's say sort of F belongs to C, say Z1, ZD. Let me try a smaller chart for a change. Say let's just do homogeneous polynomial. Okay, so then this defines a map from C to the D minus 0 to C star, and this is a vibration, smooth vibration. It's called the Miller vibration, and then the fiber of F equals F, well, equals F inverse of 1. And we call it, this is the F, this is the Miller fiber. Okay. And so in terms of this picture, this would be like this map here from X. So X, this is X, and this is X. X be just the complement, not 0, minus V of F, minus F equal to 0. Okay. All right, so X is the complement of the hypersurface here, like that, and this is C star. And then so this nu will be something from pi1 of X to Z, okay, and X nu is homotopic to F. All right? Okay, so that's one example. Okay, maybe we'll do a couple more examples. Well, the kind of the simplest example I just talked about, this would be just from R to S1. Okay, but what if I do something like sort of S1 wedges 2? You see, then the cover would be something like that, right? Be a line here with a string of balloons, right? So you see kind of a difference, a conceptual difference here. This is contractible here. This is just I want to get to a point, whereas this has a second Betti number infinite, okay? So you have this infinite cover. Sometimes they have finite Betti numbers. Sometimes they have infinite Betti numbers, okay? So what I'm getting at is try to kind of understand conceptually kind of for all such covers and understand which ones are of this type, have finite Betti numbers, and which ones have infinite Betti numbers. And you see, for example, here in this geometric situation, this is you can think of this Milnor fiber as being an infinite cyclic cover of the complement. It wants to have infinite Betti numbers, right? I mean, why should infinite cover have finite Betti numbers? I mean, typically it should be something like that, but it has finite Betti numbers. It has the homotopy type of a finite complex. Okay, so why?
Because Milnor proved it. There.
Well, right, but it's not kind of obvious, right? No. So, okay, so all right, so that's more or less the setup. I could look at all possible covers for technical reasons, and you see, in order to have a good theory, I just restricted to 3 abelian covers. Although it would be interesting to try to generalize this theory to, say, first arbitrary abelian covers, and then even more generally. So, okay, so now let's see, right? Remember, this is kind of our input data. We have this epimorphism from G to Z to ZR. This is new. Now it factors to the abelianization because this is an abelian quotient, so it factors to the maximal abelian quotient of G. So okay, and so let's write this new star. So this is H1 XZ. And this is this H1 of T to the Z. So this is what I had before as, let's also write this new star. And this is in H1 XQ. All right. Okay, let me just write this new star. Okay, so So this cover that we're talking about is determined by this normal subgroup, kernel of nu, inside this normal subgroup inside G. Right? Up to conjugacy. So this is this kind of classification of connected covers of a C-W complex. But now this kernel is determined by the kernel actually of this map nu star from H1xz to this map, which is Z to ZR, right? Once you know this map, you know this is just a composite of this with this abelianization. And furthermore, this is determined by the kernel of the map with rational coefficients. Okay, and this is a all right. This is see, this is Q to the n, say, and this is onto, right? Okay. All right. Which, by linear algebra, this is just the image of the transpose map, which is the map in cohomology, H1xq. So I did all these kind of things just to for some purpose, you know. So anyhow, so the upshot is, which goes back to this paper of Dwyer-Fried that I'm going to mention from 1987. So this is how you parameterize this regular connected regular Z to ZR covers of X. This is this set that I'm trying to understand. Are in one-to-one correspondence. Well, let's see. So this is now, this is injective, okay? And this is Q to Zn. So by the way, you see here, I'm just going this way from this map, this integral map. I go to this rational map, but the other way around, I just I have this space. I just pick an integral basis because the map is defined over Z. Okay, so you have this rational subspace. You can find an integral basis going back the other way around.
Yeah, I was going to ask that when you took a breath, like why? I mean, that's not free ability necessarily. So I don't understand why knowing the kernel of the rationalized map would tell you the kernel of the one with Z coefficients.
Well, it factors through further through abelianization modular torsion. So the torsion just go to 0 under this map, so you don't care about it. Okay. All right. Well, good question. Okay. So therefore, this is an injective map. Look at kind of all the possible subspaces Q to ZR, and Q to Zn. So this is just the Grassmannian GR, say Q to Zn, or H1xq. Okay. And the correspondence goes, you have a cover like that, like I was talking about. This goes to this P nu, which is this image of nu star. Okay? So one more time. So given a cover, you just do this procedure I was talking about, and you find a certain plane, an R plane inside R to the n, in Q to the n, a rational plane. And conversely, if you have a rational plane in the space, in the rational space spanned by of dimension n, where n is the first Bethe number, you can find an integral basis and go backwards and find a cover. Okay, so that's kind of the parametrization. Okay. So that's sort of like a moduli space, and now I start moving about this around this Grassmannian, which is a standard object in algebraic geometry, and try to understand qualitatively discovers.
Is that Bill Dwyer at Notre Dame?
Yes. Okay, so that was actually, very short paper, 3-page paper in BLMS.
Does it basically go just like that?
Well, I mean, they say these are the first 3 lines in the paper or something. and then there is, proof using commutative algebras. Okay, but let me first make a definition. Okay, so definition. So let me define following, what they do there, the following sets. The Dwyer-Fried invariants, and I'm going to explain the terminology in a second, of X are the subsets so they depend on 2 parameters, omega IR of X equals, let me think, okay, let me just write P nu. So they're subsets of the Grassmannian of R planes in n-dimensional space such that the Betti numbers of X nu are finite in the range from 1 to I. Okay? So I'm moving in the Grassmannian. Okay, so I fix an R here. Okay, so I'm looking at all free abelian covers of rank R over my space X. Okay, and I start computing the Betti numbers, right? You just now it's again a C-level complex. You can compute the Betti numbers up to a certain range I. Here this is a homological index, and if they're all finite, you win. It's an element in the set. If not, one of them is infinite. It's not. Okay. So that's the object of the talk. Okay, how to understand these sets. For some reason, I think there are some interesting sets. So, so they define for I greater than 0, I greater than 0, with convention let's see, omega I R X equals empty set if R is beyond the Betti number, okay? Because the Grassmannian is empty. For fixed R, get filtration. So you start with the Grassmannian. N is again the Betti number. This is omega 0. Let me drop. And then you have omega. It's a decreasing set, right? Decreasing sequence. Okay? Because you ask for more and more conditions. Okay? The first Betti number, second Betti number, and so on. Right? The 0 Betti number is always 1, right? Because these covers are connected. So there is no condition. But from the first Betti number and on, you start adding conditions. Okay? They are homotopy type invariants. Of a space X, namely, if you have a homotopy between X and Y, a homotopy equivalence, well, without loss of generality, you can make it cellular, and then this induces a map between H1 Y in cohomology with Q coefficients. Okay, so this is an isomorphism of groups, and that induces then a map, let me not give it any name, between the Grassmannians. Okay, when you have actually this is an isomorphism of vector spaces, so you get an isomorphism between the corresponding Grassmannians, right? And then there is an exercise that, tracing through these naturality properties and all these kind of identifications, that this isomorphism preserves the sets, these Dwyer-Fried sets. Okay? and this is a bijection. Okay, so right now I have no structure on these sets; they're just sets. Okay, I don't claim they are any kind of algebraic structure. In fact, in general, though, they're not. They don't really have a kind of nice structure. They're just sets. But in some special situations, they have more structure. All right? Clear? So that's why I call them invariants, okay? Because up here they're just sets, but because of these properties, they are invariants of the space. So, so thus may extend definition to groups. So you can also talk about the Dwyer-Fried invariants of a groups, right? You just declare, say, for G finitely generated group. Remember, as the X has finite one skeleton, so at least I have, this first homology to be finitely generated. So I ask the G to be finitely generated, then I can define these sets to be the sets associated to a classifying space of the group, an Eilenberg-Margolin space. And because these are homotopy type invariants, it doesn't matter which KG1 I pick. Okay? So I define for you now some sets which I can associate to any space or any group. Okay? And the question is, how on earth do you compute these sets, and what are they good for? Right? And I'm trying to advertise they're very natural. They should be in manuals. I mean, like because they seem like in basic manuals, right? When you textbooks, right? You're writing textbook, right? Would you put this in a textbook?
Not in the calculus, but maybe the technical details.
Okay, all right.
Can you program mathematics?
Well, I mean, you can write cell structures. You can compute, homology. You just compute, you just row-reduced matrices, right? That's what compute Betty numbers, right? You have to do Gaussian elimination. I mean, so, all right. Let me maybe skip this, or maybe how about I just quickly? So, simple situation. R equal n, right? The extreme when R equal n, the biggest it can be before it gets totally trivial. So then we have grn of h1xq, which remember this is q to the n. This is just a point, right? How many n spaces are in n space? Just a single one, so just a point. So this corresponds, remember there is this correspondence between points in the Grassmannian and covers. This corresponds to x alpha x. This is the maximal torsion-free Abelian cover corresponding to G goes to G ab. This is what Dave was asking about, G ab modulo the torsion. Okay, so this is this covering. Okay. All right. So here omega I n x equals empty or the whole thing, according to whether this cover has some Betty number infinite or all the Betty numbers are finite. Okay, so e.g. Omega I1 of, say, S1 wedge Sk. Can you tell me what this is? So remember, this is now the pi1 equals z, right? So this is this exon. Right? You have this string of balloons here, right, which are just SKs. So up to degree k minus 1, the Betty numbers are finite, right? They're actually 0. So this is what? It's a point for I less or equal than k minus 1, But once you hit k, right, bk is infinite, so this is empty. All right? Okay. And I put here 1 because that's the only degree, r equal 1, because that's the first Betti number. There is no other abelian cover. Well, up to, that's the only rank of an abelian cover, 1. All right. So you see, in some very simple examples like that, you can completely understand these sets, but you do something slightly more complicated, it becomes a non-trivial problem. Okay, so here is the idea how to actually kind of do this in the smart way. Maybe I'll skip. Should I tell you about this? Should I do this?
Decide whether to tell us how to go about it in a smart way.
Well, okay, I'll do a remark. Maybe I'll skip a remark. I have a remark about knot theory and the Alexander polynomials, but maybe I'll skip it. I'll tell you more if you ask me at the end. Let me kind of plunge ahead and tell you how to actually do it, all right? So to do this, the characteristic varieties, we try to kind of understand these sets in terms of some varieties, okay, that we can compute by methods of commutative algebra and algebraic geometry. So let's look at, let's look at before g equal pi on x, as before. Let's look at the character group. Right, so these are just the group homomorphisms from G to C to the non-zero complex numbers. This is an algebraic group with the identity component C star to the n. So this is the component of the identity. And the other components are isomorphic to the identity component, and they are parameterized by the torsion elements in G-ab. Okay? So note G-ab, this abelianization map induces an isomorphism. This goes the other way around. All right. So this character group just depends because this is abelian, so every homomorphism factors to the abelianization. So all this gadget cares about is the abelianization. Okay, so it's not a very not a very sophisticated invariant of the group of the space, but again, it parameterizes things. Okay. So what does it parameterize? So G hat parameterizes now. It doesn't parameterize covers anymore like the Grassmannian. It parameterizes rank 1 local systems. Rank 1 local systems on X. So if you have a character, it determines L rho, L sub rho, which is C, viewed as module over the group ring of G, ZG, via, let's say, right module. So I want to say A times G equals rho of G times A for G in G and A in C. Okay? So, I don't know, maybe they would call them locally constant rank 1 sheaves or something. Yes. Oh, yeah. Okay. So as you go around, you see you have your space, and this is X, and you have loops here. So you have this base point, and you this would be a G, an element in the fundamental group is just a loop based at x0. And you think of having here, this is your L. And then as you, which is C, and as you move along this loop, as you come back, you get this row of G, which is element in C star, and you multiply C by that complex number, okay? All right. And then you can define, and then sort of define the homology of X with coefficients in this rank 1 local system. This Schiff homology is what? Is the homology of, you take the chain complex of the universal cover, which is a chain complex of left ZG modules. Let me do in homology right now. Okay, you can do both versions, but let me do homology. Okay, all right. Okay, so this is equivariant chain complex of universal cover. Right. So again, this is it's a CW complex. The fundamental group acts on this cover. It's a regular cover with a group of the transformations G. So it acts on the chains. So this is a chain complex of modules of a ZG. You take this module and you tensor it with this rank 1 local system. You get now a chain complex of vector spaces, and then you compute the homology. Okay. Maybe I'll do an okay, I'll do an example in a second, or maybe 2 minutes. Okay, so now definition. Let me first make this crucial definition here. So these are now the characteristic varieties of X. Okay, and I don't give you the most general definition, just the one that we need for the purpose of this talk. So again, this would be now my parameter space, right? You look at all this homomorphisms, right? Or these rank 1 local systems. Each one allows us to compute homology, and again, you do something with this homology. You record.
Is that a script V?
Yeah, right. V for variety. Yeah. Okay, so I'm looking at a row inside this character group, and I want, okay, so Hg of X with coefficients in this, say, line bundle, if you want, to be not equal to 0 for some j less or equal than I. Okay? And they're defined for I up to degree k, where, say, if X has finitely many cells up to degree k. So you want some kind of fineness for X in order to be able to define this. I mean, I can make the definition general, but if that happens, these are actually varieties. So let me write it down. So sort of get filtration. They include a trivial character. Say, let me write it here. X has finite k skeleton. Let me just, for some k. Adding this hypothesis, some kind of finiteness hypothesis. So I have then a filtration. 1 is V0, included in V1. Okay. All right. So each vi of x is a Zariski closed subset of the algebraic group G hat. This is an algebraic. This is itself a variety, so you take a subvariety. Okay. And again, it's not totally obvious. You have to do kind of a computation here with minors. Realize that the places where
G having its structure is a torus.
right. Yes. Okay. Let's say 1 belongs to vi of x. Okay, no, let me just kind of skip that. Okay, and then the characteristic varieties are, again, homotopy type invariants. They just depend on of x. Right, yes. I mean, again, so if you have a homotopy equivalence between two cellular complexes, you can assume it's cellular. It induces a map between fundamental groups, right? You can see it coming, everything kind of, right? And that induces an F-sharp hat between the other way around, between the character tori, and then you have here this vi of x prime, and you have this vi of x sitting inside, and you get a map this way. This is an algebraic isomorphism, and it restricts to algebraic isomorphism between these varieties. Okay?
Does isomorphism have a lot more structure to it because of the cellular nature of the map it's giving it to? No, because you can kind of move it.
No, you shouldn't think. I mean, these varieties can be, quite complicated. I mean, they're about as complicated as they are determinant varieties.
Determinant.
Right. They are given by some rank conditions on some matrices where this homology vanishes. But except for that, they can be quite complicated. Although in natural situations, there are various structure theorems about them. Let me do a very simple example for those who never seen this definition before. Let's work it out from scratch. Okay, let's do the simplest example in nature, namely x is the circle. Okay, so Dave, okay, no. let's do it together.
No, it's not. Oh, I've seen it before. You should ask them.
All right. So the universal cover is R, right?
I could have done that.
Okay. Okay. So pi1 of x, let's say with a base point, this is just z, right? Okay, what I want to say. And then sort of z equals is the Laurent polynomial ring. So let's say with generator T, okay? All right, and then we write C star of x tilde. Well, this is C1 of x tilde. It has only 1 cells and 0 cells, right? And that's delta 1. Well, that's ZZ, and this is ZZ, right? Because the circle has a single 0 cell, right? This is E0, this is E1. This is the base point, okay? All right, and then what is the boundary map? It should be a polynomial in T, right? What polynomial? How about T minus 1, right? Because you go, the boundary here of the interval, this is 1, and then you go T, right? With opposite signs, so you get T minus 1. Okay, so that's the equivalent chain complex. You see, so this is S1. Let me kind of turn it around, right? This is R, which is S1 tilde. Maybe you'll see it better, right? So this is E0 tilde. This is E1, E0 tilde, say 1, and this is T, E0 tilde T inverse, right? And this is E1 tilde and so on, okay? So what's delta E1 is E0T minus E01, which is T minus 1 is 0, if you want, with these identifications, okay?
It's so hard to translate from your language to mine, and vice versa.
All right.
Yeah, it's the monotropy minus the.
Okay, very good. All right. So now for rho belongs to what? We have to kind of give sort of z hat, which is what? Home, remember z c star, which is c star. So now the character torus is just c star, so you just pick an element in c star. Then we're doing what? We're supposed to do this gadget, right? Remember, over ZZ. So what is that? You tensor this over ZZ with L rho, which is a C, right? So you get C. And here you put C. And what do you put here? You just evaluate this polynomial at t equal rho. So it's just rho minus 1, right? Okay, and now you have to compute the homology of this chain complex. So this chain complex is exact. In other words, rho minus 1 is invertible for every rho, for all rho, except what? Rho equal 1, right? Which is kind of the only eigenvalue here. Okay, and so therefore V0 S1 equals V1 S1 equal 1. Okay? That's the only place where the homology jumps, okay? So which are exactly the Betti numbers of S1, 1 and 1. And then everything else, this chain complex is exact, so there is no homology, all right? Okay, all right. Okay, I'm getting there. Let me just, before let me give you one other interpretation of this characteristic, sort of another interpretation. Which is sometimes more useful from the point of view of commutative algebra. Vi of x is the support of a certain module okay, all right. So this is, remember, this is universal abelian cover. So you take the homology of the universal abelian cover up to degree I. So that's a module over Z G ab. Okay, and now you take its support variety, which means you take the annihilator, which is an ideal in this ring, and you take the variety defined by that ideal. Okay, and it turns out that this characteristic varieties. So the spec of this ZG-ab is exactly this character group, G hat, sort of subvarieties in spec G-ab. G hat. Okay. All right. So this is, I mean, various variants of this theorem. Maybe in degree 1 was first proved by Eko Hironaka. We heard of talk here before, and then this generality, it's a result in a recent paper. It just appeared with Stefan Papadima. Okay.
The last name.
Oh.
I knew that
Okay.
The last name, is that Soto? 2010. Oh, 2010. Oh, sorry. Sorry. Oh,
Okay.
sorry. Got it. Yes.
Okay.
Never mind. I can see why you were confused.
All right.
It's what a whole math conversation.
Okay. So so analogous result. So for technical reasons, actually, we're just going to use this Wix, which are just this Vix intersect this, just the torus, the identity component. Okay. So so this is just included in C star to the n. Okay. So that way you can ignore the torsion part. So here you just put this X alpha, the maximum torsion free abelian cover. Okay. All right. So now let's put together the two strands. Okay, so theorem. So this goes back to Dwyer-Fried in 1987, and then kind of was updated and kind of translated in this language and a little bit more general in this paper I just mentioned with Papadima and myself in 2010. Okay, so this is a theorem. So let x nu x be a free abelian cover given by, as you remember, by sort of mu from pi 1x to z to zr by an epimorphism like that. Okay, and I remind you this was g. Let, say, t nu equals nu hat, sort of the image of nu hat. So nu hat goes from what? From the character torus of z to zr to g hat, right? And so this is a c star to the r. Okay. So then, dim of this kind of module summation of hj x nu c. Let's just see. So the sum of the Betti numbers of this cover is finite if and only if this torus T nu intersect. Okay, so this torus lies in this C star to the R. Not R, a mistake here. This should be. Oh no, it's okay. It's a C star to the R, but you see it sits inside C star to the N. I meant to say. Okay. Right. So this image lies in G hat, which is a C star to the N. Right. So you have this R-dimensional torus here. And you also have this characteristic variety here, which also lies in C star to the N. So you can intersect these two subvarieties. And this should be is finite. Okay? So one more time. You see you have now this is this G hat, okay, which it's a complex torus, okay? And it has a distinguished point, the origin, the trivial character. And inside here you have this, okay, this is this T nu, right? Which is the C star to ZR, okay? It's a subtorus, okay? That passes also, it's an algebraic subtorus, right? But you also have, okay, you may have some other components. Okay, so this is Wi, all right? That you compute by some other methods, all right? And then you look at the intersection, and you say if that intersection is finite, then you win, right? This sum of the Betti numbers is finite. Otherwise, it's infinite, okay? Kind of, that intersection kind of counts the Betti numbers.
I have to look back or ask you. I mean, a number of times you said, oh, everything's well defined because if two things are homotopy equivalent, you get isomorphisms.
Right.
But that doesn't mean that the intersection is well defined because you might have taken different isomorphisms into the space. But there were canonical, you get a canonical thing. And the point is that it's just, I'm worried about this intersection meaning anything if those two things are only defined up to like isomorphism inside of something. That doesn't mean the intersection is a well-defined thing.
But whether it's finite or not, I think it's well defined. That's what we're worried
Yeah,
No,
but this
I
W
think
is
two varieties missing, intersecting the finite set, and then isomorphic copies intersecting infinitely.
Yeah.
But there were canonical
Yeah, but
embeddings. It's just the
yeah, but not. This is canonical. This just
Okay.
depends on X.
Okay.
This depends on this nu. But you see, if you take a homotopy equivalence, it may change the kernel of nu. So that may move the
it's only
torus.
moving
It may change the cover.
right, but it's not changing whether that intersection is finite. Right.
And that makes me a little bit nervous.
Makes me,
Yeah, if it
But
changes,
like I
if
said,
it
I
changes
have
the
to look back
cover,
at everything
right?
you said.
Yeah,
I'm just
yeah, I would
wondering
have to
whether
think.
that- I'm wondering whether that can.
If it changes the
I'm wondering
cover,
whether that
then.
condition is invariant under all the things you've said, and I can't decide quickly.
But I haven't made any. I mean, here I'm just fixing nu, right? I'm just fixing a nu, and I say, I'm looking at this particular torus that fixes this cover.
Right. Well, what I can't remember how many things depended on things like the homotopy and how many didn't. So,
Okay, so let me now reinterpret this. Okay, so this is kind of so reinterpret this as let me write this. So this is kind of this this paper that I'm writing.
And so do again.
That same, you work a lot with that recently.
All right. So this is, okay, so it kind of cuts off all this kind of news and stuff. Okay, this is going to look more invariant to please Dave. So this is with no ifs and buts. Okay. So remember this is this Dwyer-Fried sets which are subsets of the Caspanian, and you just take X P tensor C, you take a rational r-dimensional plane in this Q to the n, you exponentiate it, right? And then you intersect it with Wy with X, okay? It's finite. This set, okay? So basically this is this torus here. So let me just maybe put a picture here. See, this would be in the tangent space here, this is 0. This is C to the n, right? And this is let's just say that this is G hat 0. I just care about what happens in the component containing the identity. And this is the exponential map, right, of the tangent space C to the n to C star to the n. And here I see a plane P, a rational plane, whose image, you see, sort of this is P equal P nu. Okay, the image of this is this torus, okay, or its complexification. And okay, so basically I kind of eliminate this T nu. I write it as the exponential of some plane here. And then with a little bit of chasing diagrams, you just get this kind of clean formula for these sets. Okay, so let's derive some quick corollaries. These are kind of two extreme situations. What if W, this characteristic varieties, is finite? then these sets are the whole thing. Okay, let me just write q to the n, right? Because there is no condition, right? And this happens, for example, sort of e.g. if X is a nil manifold, e.g. a torus, in which case it's obvious, or X is a product of knot complements. Okay, so for many manifolds, you can show that actually this characteristic variety is finite. So immediately it says that all Fiabilan covers have finite Betti numbers. And at the other extreme, suppose that Wi of x is infinite. Well, then it becomes more complicated. But at least you can say this cheap corollary that this is the empty set for every q greater or equal than I. Okay, but you see here I took the maximal one, remember? So this is when you're taking the Fiabilan cover of X. That's the one for which this is the whole C to the n, so this is the whole thing. So it intersects Wi X into an infinite set, okay? Okay. How much time I have?
I think you started about 10 after.
Okay. So give me okay, let me, okay.
6 minutes, but you have to go over by another 5.
Let me try to kind of, where does this go now? Okay, so basically this is just taking this stuff from, 87 and kind of updating it here and kind of in this context, but you know, what is kind of more modern here and where does it go? So let me just go to tangent cone upper bound. Okay, so I'll be a little bit more brief here. So, so first of all, let's just say that W equals V of I Zariski closed subset of C star to the n, like this Wi of x, okay? See, this is kind of this mysterious quantity. I'm trying now to approximate it, okay? You can define two approximations. One is two approximations. One is classical, goes back to at least Whitney, or maybe even further, the tangent cone, which is the variety defined by the initial ideal, phi. Okay, you take a finite set of polynomials here, and then you take, well, actually, you take the initial forms of all the polynomials in I. Okay, and take the variety defined by that. So this is the tangent cone, and this lies inside C to the n. But you can also define which is something we call a exponential tangent cone, which is z inside C to the n, such that x lambda z belongs to W for every lambda in C. Okay, so this is a definition that goes from a recent paper with Alex Dimpa and Stefan Papadima and I. This is 2009.
Can you call that what? The exponential?
Yeah, this, right, exponential tangent cone. So actually, this is better behaved for our purposes. They're both, they're all homogeneous subvarieties. They depend just on the germ at the origin of W. They commute with finite unions. This guy commutes with arbitrary intersections. So facts, tau1 of W is included in TC1 of W equal if W equal union of subtori, but not equal in general. And I'll give you a quick example. And but what's nice about this is this is a finite union of rationally defined subspaces, okay, which can be computed explicitly. Okay, so maybe I'll give you a quick example. Let's say that V equals V of T1 plus T2 minus 2. Okay, inside. So look at the vanishing set of this polynomial, T1 plus T2 minus 2. So this is an exercise you can give to a calculus. It's a calculus. This is what? T1. T1, right? These are coordinates, right? Okay. So Dave, okay, this you can, if somebody read your calculus book, should be able to compute this exponential tangent cone, right? Well, let me do it for you. It's you look at the z, by definition, right? Such that e to the tz1 plus e to the tz2 equals to 2, right? Now you expand this in Maclaurin series, okay, and you look at the quadratic term, and you see z1 squared plus z2 squared equals 0. So this means just 0, okay? But if you take tc1 at w, the tangent cone, you just get z. This is z1 plus z2. You get a line. Okay, so this is bigger, right? So that's, I think, an instructive example to do, and it's it's a kind of a cute exercise to kind of compute this subspace arrangements associated to an arbitrary set like that, that is a closed subset of the torus.
You kind of said that house of one being a finite union of rationally defined subspaces is an advantage of it, but the initial forms are computable. Right?
Yeah, but they're kind of nonlinear. They're actually still complicated, and they're not very well at that. Well, the proof is in the pudding. I mean, for the theorem that I'm trying to prove, this guy is better. Okay? Because remember, I had this exponential map. And that kind of ties it up much more closely to the set itself than this tangent cone.
Geometrically, the Whitney's tangent cone is the union of the secant lines.
Yeah.
Right? What is this one geometrically? Is it easy to say? It is what it is.
It's kind of, the lines which exponentiate to this subtorade that sit inside your variety. So I don't know, it's kind of, you pick up the directions, that's sort of the directrices in your set.
Yeah.
Okay?
Oh. Okay.
All right, so let me kind of maybe finish with this theorem then. And then say a few more words and stop. Oh, maybe I should say first, I forgot to say, theorem. Okay, how about this? I just created a theorem. The way I started it is included in, and I'll make the definition in a second. Okay. All right. So this is a much easier thing. It says, well, this is not inequality in general, but it's an upper bound, which is easier to compute. You just look at the planes which intersect certain subspaces not equal to 0, and where CI of x, where is defined, well, you take the exponential tangent cone to this characteristic variety. It's a union of subspaces, and you just write it, right? You just write it as L tensor C over L belongs to Ci of x. So essentially, this is just this. You look at this exponential tangent cone to this characteristic variety, okay? All right. All right, and then I say just maybe because I mentioned this in the abstract, I say a couple of words and I'll stop. Now, what is this right side? Okay, so, okay, in other words, this can be written as following. Omega I of x is included in this Grassmannian. Let me just write it, q to the n, minus the union. So this is a well-known thing. This is like this. Okay, sort of where sigma r of L this, okay, let me just make sure I wrote exactly, okay, is the special Schubert variety associated to the subspace L. Okay. So let me just contemplate this equation, say a few words, and then I stop. I won't write anything more on the board. So this is now this upper bound. I kind of went through various stages. This is now, these are classical Schubert varieties. People study a lot. These are, you look at the planes which intersect a fixed subspace, okay? These are kind of the simplest Schubert varieties in a sense. The flag consists just of a single subspace L here. So you take a union of these Schubert varieties. So this is now a Zariski closed subset in this Grassmannian. The complement is an open Zariski open subset. So this Dwyer-Fried invariants, which are very mysterious, that record all these topological properties of a space and its covering spaces, are included in a certain Zariski open set. In general, this inclusion is strict though. These sets, these guys, these are not open in general, even when X is a compact Kähler manifold. So, but for many spaces, one can show this is so-called straight spaces. One can show that this is an equality, and then this can be expressed in terms of some simpler data, just in terms of the cohomology ring of X, in terms of something called the resonance varieties of X. Okay, I'll stop here.
Are there questions, comments, anything?
You fed us a line so that we'd ask questions. I'm ready to do that. But anybody have a question or a comment? So what about knot theory and Alexandru polynomials?
Oh, yes. Okay. Now that you ask me,
is it short?
Actually, I can say what I've been writing. So. You know, I just look here at the Betti numbers, the findings of Betti numbers, but you can ask a subtle question. Are the homology groups finitely generated as abelian groups? Right? And the answer is different. So for knot complement, you can have knots for which the knot is not fibered, and for which the universal abelian cover, the homology groups are H1 of the universal abelian cover is not finitely generated as an abelian group, although the Betti numbers are finite.
And that's useful to look at?
Yeah, of course.
Dwyer-Fried.
I mean, this is an example, this is an example due to Milnor. Actually, Milnor, in 1968, when he wrote the book on singular points, right? He also wrote a little article called Infinite cyclic covers of knot complements, where he studied this problem. And you know, he he takes K, this knot, okay, this so-called 5 to torus knot.
I couldn't draw that fast.
So this is the Alexandru polynomial.
Your hand is hurt.
So, okay, so you see this has h1, so x is s3 minus k, right? h1 of x is just z, so you have this abelian cover, right? What is the h1 of the universal abelian cover? This goes back to Alexander, how he defined the Alexander polynomial. This is just z plus or minus 1 modulo. It's a cyclic module, right? And the Alexander polynomial is the order of this module, right? So, but this is, as an abelian group, z a half plus z a half, not finitely generated, okay? But B1 of x ab is just, it doesn't, see, that's because the leading term of the Alexander polynomial is 2. The Alexander polynomial is not monic. That translates in this homology group being kind of complicated. But if you tensor with Q, the difficulty disappears. This is just the degree of the Alexander polynomial, which in this case is just 2. Okay? So for knot complements, the Dwyer-Fried set is always non-empty. It's the same thing. It doesn't matter whether the knot is fiber or not fiber. So what I'm trying to say, what I'm doing here with this Dwyer-Fried invariant is a simplified theory by just looking at the Betti numbers. We don't look at the final structure. Okay? And then there is a given final structure by looking at the finiteness properties of the groups. And that you have to look at this so-called Beery-Neumann-Strebel-Renz invariants, which are even subtler. But the same kind of theory with further modification applies. But that's a different story.
We've got another hour. Are there other questions, comments?